तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture we saw two programmable logic devices, namely PROMs, programmable read only memories, and PLAs, programmable logic arrays. A minor variation of the programmable logic array is called a programmable array logic. We will see today programmable array logic, also known as PAL. This is by far the most popular programmable device that is used for design in the industry. The difference between programmable array logic and programmable logic array is rather simple. In the ROM we derived all the minterms possible for a given set of input functions and combined those minterms in the OR gate array to get the functions required. Later we decided it is an underutilization of the minterms because many functions the output use only a very small number of minterms. So, instead of producing or generating all the minterms, we will only generate a fixed number of a required number of product terms and combine these product terms to get the required functions. In so doing, we try to identify as many common terms as possible. The same concept of reducing the function to get a few product terms rather than all the minterms will be followed here. That means approach is similar. So, we will program the input variables into a few product terms which are required for implementing the functions. But what is different between PAL and PLA and the PAL is, in the PLA we had the OR gates in which we can combine the product terms whatever way we want. On the other hand, in PAL the OR gate connections are fixed. You have no choice on the what product term, you have no choice on what product terms go into make a different function, make a specific output function. So, here we have the opposite of, or not opposite, slightly varied version of programmable logic array. This is the PAL structure. We have the inputs, generate AND array as we did earlier by programming to get some product terms P n maybe, and put them in a OR array the OR array has output OR gates to which we can give the min terms or the product terms as input. The difference lies in the fact that the OR gate inputs are fixed. That means we can only have a specific product term as input to a particular OR gate. For example, if you call this F1, F2, F1 will say, they will say P0 and P1 alone will be connected to F1. You have a choice of implementing P0, P1 using a programmable AND structure from the inputs. So, any combination of the input structure to get P0, P1 is possible, but once you have done it, P0 and P1 are fixed inputs to the OR gate, you cannot have any other input. So, this OR gate will have only 2 inputs, and these 2 inputs are also fixed. These inputs are namely in this case P0 and P1. Likewise, they may say F2 will have P3, P4 and P5. Let us have n is equal to 5 in this case, n is equal to 4 in this case, that means we will call this P2, P3 and P4. So, P1, P2, P3, P4, which means my F1 is P0 or P1, F2 is P3, P4. Now, we have removed a certain amount of flexibility from the OR array. Earlier the OR array was programmable, any combination, any number of the product terms that are generated could become inputs to the OR gates. In this case though, the inputs, number of inputs as well as the product terms that are connected to the OR inputs of the OR gate are fixed. In this particular example, F1 can only take P0 and P1 as inputs, F2 can only take P2, P3 and P4 as inputs. That means I am restricted in what type of functions I can implement. F1 and F2 can only have 2 product terms, it is a sum of product expression, 2 product terms allowed. In this case a maximum of 3 product terms is allowed, and these product terms themselves can be variable because I can program it the way I like in AND array. So, this OR array is a fixed array, not a programmable array. This OR array is a fixed array, not a programmable array. Now, that means there is a slight difference in the philosophy of design. Earlier we said try to minimize the number of product terms, try to minimize the function logic functions, have as few product terms as possible, but more importance was given to the commonality. We wanted to have as many common product terms as possible between different functions, so that the same product functions once generated can be put as input to this etc. In this case, since they are fixed, I cannot the common product terms is not going to help me. Even if P2 and P0 are same, I still have to generate it once for this and once for this. So, common product terms have no specific advantage, but since I want to reduce the number of inputs to this OR gate to 2, to this OR gate to 3, my simplification will now depend on how efficiently I can reduce it. So, go back to the original corner map implementation, try to minimize the product terms, try to minimize the sum of product terms such that have as few product terms as possible, so that the OR gate, they are within the input limits of the OR gate. To summarize then, the 3 devices we have seen, 3 PLDs, one is PROM, next is programmable logic array, third is programmable array logic, AND array is fixed, you generate all the min terms, OR array is programmable, you can combine any way you like. In a programmable logic array, AND array is programmable. You can generate min terms, you can generate product terms by any combination of the input by giving the appropriate inputs to the AND gates. And OR gate is also programmable. You can combine the product terms so generated in any manner you like to form the output functions. The design concept here was to minimize the functions, but keeping in mind have as many common terms as possible. PIL on the other hand will have programmable AND gate. That means I can generate product terms based on the requirement of the function, but the inputs to the OR gates are fixed, and you don't have OR gates do not have a programmable functionality. OR gates have fixed functionality. That means to that extent it gets restricted. Once generated the product terms, which product terms, how many product terms and which product terms go into each of the OR gates is restricted. So we cannot change that. But why do we go for this from here to here? That means we are going one step backwards. This is the historic evolution. PROM was first done, and then the PLA, they found it is, this programmability was there. The reason for going for PLA was the programmable fixed AND gates generating all the min terms was an inefficient way of using the product terms as well as consuming a lot of silicon. So they thought of programming this so that we will have programmable options. So this becomes more efficient implementation wise. Then we are going backward by one step, because in this case this is too much. 2 degrees of freedom is difficult to optimize. So we have a programmable AND structure and a programmable OR structure. In order to get the most efficient implementation, too much of a, see, most of these designs are automated, you should realize this. We take simple example in the class so you understand it, but in practice the systems are huge, large number of inputs, large number of outputs. So when you design a tool to optimize, it becomes more efficient to optimize when the number of parameters we optimize is small. So that is the main reason. So what we can do is at less expensive in terms of the utility, in terms of utilization, and also in terms of programming efforts. Because of that we go to PIL. Even though we are losing a degree of freedom, it becomes easier to program manually as well as automatically. That means when something is easy to program, it is better to optimize it, easier to optimize it. So you can get better structures, efficient structures out of this. That is the philosophy for going to this. Now let us try to implement the same function we implemented yesterday using PLA and a PIL. So if you remember, those functions were F1, F2, F3. Did we call them F0, F1, F2 or F0, F1, F2, F3? F1, F2, F3. So it was F1, XY, X bar Z, F2, X bar Z, F3, XY, Y bar Z. So what we have to do is we have to have a requirement we are only talking about programmable fixed AND gates, OR gate structure. Requirement, of course, there should be 3 inputs because there are X, Y, Z. There has to be 3 outputs. So this is common to both the devices, PIL and PLA. But what has to be specified further in this case, which is not done in the case of programmable logic array, is how many inputs to the each OR gate. So we will have to say here we have output AND gates to OR gate, that is inputs to OR gate. inputs OR gate has to be specified by you. Supposing somebody gives you, of course this is a very trivial function, there are only 2 inputs required. Supposing you need a 5 input OR gate and they give you a device with 3 inputs only to OR gate, then you can't implement this function with that. So this also has to be specified in your requirement. Input OR gates in this case are 2, 2, 2. So I want 3 OR gates with at least 2 inputs to each one of them. That's what it means. So this is an extra requirement we need to say give in your specification also. So how does the system, how to design the system? Now the system is very easy. So I am going to have my x bar, y bar, z bar as you said earlier. So I generate the product terms. I call this product term P0 and P1. This is first product. First function is xy XOR z, x bar z, xy x bar z. So these two should go into my first OR gate. So my OR array, which is a fixed array, F1 will have these 2 functions as inputs. Then I go for the second function. Second function is y bar. This may P2, x bar z, x bar z, P3. These 2 go as inputs to my second OR gate. Now, the third one is xy. This is what I mean. This xy is generated already for F1. We are generating it again for F2. We have not used that what we generated already. Likewise, we had generated this x bar c for F1. We had to generate it again for F2. See? That is what it is. This is xy and y bar c, P4 and P5, and that will be the inputs to my third OR gate or third function F2. This is F2. So this is the programmable AND programmable and this is fixed R. Fixed R. So identify this as P0, P1, P2, P3, P4, P5. Each term has to be generated. So here the simplification would be to reduce the number of product terms for each output. In the programmable logic array approach, the technique would be to make as many common terms as possible. Here we have to reduce the total number of product terms into each of the inputs, so that the OR gate can be used. So, but as I said, in terms of, even though it is less flexible, in terms of design effort and also the number of inputs, you see in the earlier case, each OR gate I should be able to connect to each product term, I should be able to connect to each OR gate. Suppose I had a very huge system with a lot of inputs and several product terms generated, and each OR gate should have the capability to take as input any of those. So, the hardware, if you look at it that way, the OR gate size will be very large in the case of programmable logic array. Here we are saying only 2 inputs, so it is a 2 input OR gate, 2 input OR gate, 2 input OR gate. Earlier, supposing there were 5 terms, I should have had a 5 input OR gate, 5 input OR gate, 5 input OR gate, out of which I would have used 1 or 2 or 3. So, that way there is a cost saving also. Cost indirectly means silicon. So, there is a real estate saving a little bit, but the flexibility is removed to a certain extent, but programming is very easy now, both manually as well as automatically. So, this is why, these are the reasons why the programmable array logic approach has become very popular and has become almost an industry standard. Now, having said all that, these programmable array logic, as I said, are very popular today. They are used in many situations. So, people have worked further on it. There are variations. What we have seen is a simple AND OR implementation, AND followed by OR. So, this is the sum of products as I call it. Now, there are different types of outputs possible. So, suppose we have a what shall I say, types of programmable array logic outputs. One is OR gate, what we saw right now. So, we have many AND gates feeding into a single OR gate. This is a combinational. This is a combinational output with AND gates, inputs feeding to product terms feeding into OR gate. I can also have an OR gate output. The output AND gates, I mean input AND gates can feed into an OR gate which is inverted, which means there is an OR output. So, this is an active high combinational logic, active low combinational logic output. I can have also an exclusive OR type of output or exclusive NOR by making these inputs feed to an exclusive OR gate. XR out, XNOR out. If it is XNOR, I will put an inverter. So, I will put this bubble with a color. So, if that bubble comes, it becomes XNOR. More very interestingly, you can also have an output called a registered output. What a registered output is, all of you know flip-flops. Flip-flops store values and you can read these values along with the clock edge. Now, suppose you have a combination logic whose value has to be preserved till the next clock cycle. What do? You feed the combination logic output into a flip flop, store it into the flip flop, and when the next time the clock edge occurs, you read it off. Now, any circuit, even though we have been discussing combination logic, no system can be designed completely with combination logic, especially a system which is having some utility. Very few circuits are purely combinational. Most of the circuits, digital systems we see are sequential circuits which also use combination logic. Combination logic and blocks of sequential circuits such as flip flops, counters, etc. So, it will be nice to have in a single device a combination logic and a register. So, that is what is called a register. So, the AND gate which feed into an OR gate, instead of directly becoming the output, can be stored in a flip flop. Can be stored in a flip flop, and the output of this flip flop can be made available as the output. This is the registered output. And one interesting thing is, I can also take this output back as an input to the PAL, programmable logic. Like this, x and x bar, y bar, z bar. If this value, let us say q is some value, let us say p. One of the output variables is a p, it is a registered output variable. And suppose I want to use this p value into my design, that is what is done in a typical combinational sequential logic design. In a sequential logic design, you have the combination logic and the previously stored values from flip flops, together they determine the next output. So, this p which will be used required again for determining the next output, that can be put here as a q bar, and now I can have p, this will be q bar. So, this is p bar, so this is p bar and p. So, p bar also is available, just as a bar, x bar, y bar, z bar, p bar is also available. I can combine this in order to produce my combinational terms. This is called registered output. It is a very popular type of output in a PAL, because we have the option of designing a system which has combinational and sequential components. As I said, any digital system which is of practical utility or a reasonable application will have both combinational and sequential parts. Combinational logic will be taken care of by the array of the AND and OR. Sequential part will be taken care of by the registers which are available, the outputs of this. So, in a single outputs of this combinational logic. So, in a single chip or device, I can produce a whole system instead of having to separately connect the combination logic to flip flops. Now, I can do further than this, I can modify this by adding a buffer which I can enable it. So, registered output with buffer or enable, with enable this output P can go through a gate or enabler, or I will put it here itself in order to understand it. I can put a buffer which can be enabled by another term of inputs served by the combination logic. This is called enabled signal. So, if this enabled signal is high, this buffer will be enabled, the output P will be available here. Usually this is a buffer with a inverter, so this is P bar. If you do not want that, you can disable this. So, I have a choice of using this output or not by enabling, and this enable function by enabling this buffer, and this enable function is not a fixed function, it can be a function which is again function of the input variables, because this enable function also can be generated using the same combination logic array here. X, Y, Z, P, all of them can form part in determine the enable function. So, this option of this enable is the fifth output combination possible, output variation possible. Since it is, I use the same drawing, I will put this arrow to indicate the registered output is enable because of this extra logic that I have drawn here using this colored chalk, that is the thing. And of course, this flip flop requires a clock. Whenever you have the output of this OR gate to be clocked into this flip flop, to be stored in this flip flop, you need to clock it, and it is available as input in the next clock cycle. So, the clock input is there, but I am not showing it here because it is only just add to the clutter of the drawing here, but you should all realize that no flip flop can work without a clock. Later on, when you look at the system level, we will show the clock. The last type of input that is available is called programmable I/O output or input output, programmable input and output. This is a very interesting and important type of output function. What happens in this is, we have an option of using a given pin of the device, the programmable logic device, as either an input or an output. So, let us look at this drawing of this AND gate with OR gate as combinational high, simplest possible output structure. This is an output, combinational high output. Suppose I have too many such outputs, I do not need some of them. What I can do is to use this goes as a pin out to the external world. Suppose I have too many such functions and I do not have a use for this, but I am restricted by the number of inputs available to in my device, and I would like to have extra pins for input and I cannot create them. What I can do is to use this pin as an input instead of an output. That is what you mean by programmable input output. That means a pin or a connection can be programmed either as an input or an output. The way it is done is very simple. You have again an enable buffer here, same way I showed earlier. This buffer can be enabled by a combinational function using the combinational AND array, and if this is enabled, this function, let us call this f, gets through this as f bar. If you disable, on the other hand, by if you so make the function such that this is disabled, there is nothing here, even though there is a function f here, output of a gate which is disabled is a tri-state output, high impedance output. So, this high impedance output or a tri-state output, that means practically there is no electrical connectivity between this point and this point. This point is isolated from this point when you disable this buffer. So, that pin can now be used as an input. I can totally altogether give some other input. So, in this case it becomes a pin input pin. So, earlier it was an output pin, and if you disable this gate, this becomes an input pin, and I can give a totally different function. If it's the f, I can maybe give another function, let us say p. So, this p becomes an input to the device or your AND gate array p and p bar. So, this particular pin can be used as an output pin if there is a requirement for this type of combination logic output. By enabling this gate and thereby this buffer, by combining the proper input combination to the gate so that this buffer is enabled, output f or f bar or f bar and f, whatever it is available. And in case you do not need it, there is a redundant number of outputs and we do not need this output, I can disable this by disabling by proper combination of the AND gate. I can disable this buffer and take the output of this. This output is completely isolated from the rest of the logic. So, this pin is available to be used as an input pin, and any other input variable which you cannot accommodate earlier in your system could be put here. In this case I call it a p, and p becomes an extra input, additional input to the system. This is called programmable I/O, and this enable need not be always through the logic function, because sometimes I know I want only 5 inputs, 5 outputs, there are total of 8 outputs available, there are 3 redundant outputs I know for sure in the beginning. So, I am going to disable these 3, there is no point in trying to make a combination logic to disable every time. So, this can also be simplified to another variation where this can be an extra pin in your drawing, whereas I can enable this by this. If enable is 1, this is output is connected to this. If enable is 0, this is connected as an input. So, what I am saying is this enable function need not come from a combination logic within the gate structure and array gate structure. It can come also directly from a input that you give, enable input to the chip, that can be done. And this can, several of these redundant output pins can be connected together with this enable input, so that all of them will be available to the designer as inputs. This is a feature which is very popular because your device size, for a given device size you may want to design a system with more number of inputs and less number of outputs, or more number of outputs and less number of inputs. To match a wide variation of inputs and outputs using a given device, we use this option. If this option were not available, what you would have done is to have gone for a bigger device which can accommodate more inputs. Supposing I have 10 inputs, I have a device which only 8 inputs available, and I will go for a bigger device, and 10 input device may not be available. You may have to go for 12 input device or a 16 input device. On the other hand, if I had 4 I/O pins which are not, and 2 of them only going to be used output, 2 extra pins are available to me, by making this I/O option, these 2 extra pins can be used as input. So, I will have 10 inputs possible without having to go for a bigger device. So, this is a great advantage in this type of output variation, output feature. Now, having said all that, we look at 2 commercially popular devices just to show to you how these things are done in practice. So, we will take a very simple device called 16R4, which is a very popular device. I am not giving any manufacturer's name in this because several manufacturers make similar devices. Without mentioning any manufacturer name, I can give you the type number, this the part number as they call it, like 741 op amp you say, is all of you know it is an operation amplifier, but 741s can be made by different manufacturers. Similarly, 16R4 is a generic programmable logic device, or PAL, and which is manufactured by many vendors. I want to take this as an example to just show you how the chip is organized. OR means is a registered output. 4, there are 4 registered outputs, 16 for inputs. Usually the first number is the input number of inputs, second number is type of output, and third number is the number of outputs. So what is done is, in this case, let us draw this as a, I am not going to draw this as a structure, I am going to draw it as a block. This is my 16R4. It's a 20-pin device. Any device needs a ground and VCC, power supply, VCC and ground. So this is numbered from here 1 to 10, 11 to 20. This is 10. This is ground, pin is 10. 20 pin is VCC, power supply. Yes. What do you have?
20 pin.
Yes.
IOS themselves had for 20. Then value of
Yes, we will look at this. This is how it is organized. One is the clock. You will see the explanation as we go along. One is the clock pin. Clock is required, as I said in the previous case, in the registered output case. Remember, you had a flip-flop requires a clock, and I didn't show the clock at that time because I didn't want to clutter the drawing, but no flip-flop can work without a clock, so I need to provide a clock which is common to all the flip-flops. How many flip-flops are here in this case? 4, because it is a 16R4, there are 4 registers, so all the 4 flip-flops require a clock. This is a common clock for all the 4 flip-flops. Now, there are 8 pins available here which are used for inputs I1 to I8. So, pin number 2 to 9 are used for 8 inputs I1 to 8, and I also said there is an output enable. Whenever you want the input output to be used, input output combination, input output choice of certain unused outputs. I said one output enable can come either from a combination logic block or from a simple pin out. This pin will provide the enable for the buffer. So, this case, this is a simple pin enabled buffers. So, this output enable enables all the buffers which have programmed IO feature. All the programmed IO types are enabled or disabled by this OE. So, we need one pin which is similar to clock, which caters all the 4 flip flops. This will cater to all the programmed IO pins. So, that means there are 8 more left, and we still have the wonder how I am going to accommodate 16 inputs. Very easy. Now, out of these 4 are registered outputs. 4 registered outputs are pin number 3, that is registered outputs would be, this is 11, 12, 13, this will be 14, 15, 16, 17. Pin 14 to 17 are 4 registered outputs. which are counted by the, which are serviced by the same clock. And how many pins are now left? 4 pins. These 4 pins are programmed I/O pins. So there are 4 programmed I/O pins, 4 register output pins, 4 registered we said no. How did you get the 16 number now? These are 8 here, 4 here and 4 here. So all these 4 can be used as inputs. All of them can be used as inputs also. So this 16 is a sort of a trick that the manufacturers play on you. You cannot have 16 inputs and 4 outputs at the same time. 16 is the total number which can be used as input. If you use all of them 16 as inputs, no pin will be available as output, because we need 4 pins, 1 for ground, 1 for clock, 1 for VCC, 1 for an output enable. 4 pins are already gone. Totally 16 is remaining. Out of 16 I can use all of them as inputs. Where do you get the output from? Nowhere. But if you use only pure inputs and not use program features, registered features, these registers have inputs, remember that. Remember? The registered output, each registered output also caters to the input. So these 4 outputs or registered outputs also act as inputs, because they are fed back. Look at the drawing there. Any registered output also acts as an input. So 4 inputs extra, these 4 outputs, though this is counted as 4 outputs and 4 inputs, which is reasonable, nothing wrong about that. What is the trick is the other 4 can be used only either as inputs or outputs. If I use them as outputs, I do not have them as inputs. If I use the input, they are not available as outputs. So that is why he is not totally wrong, because R4 means 4 registered outputs. These 8, these 4 are, even though they are 4 registered outputs, all the 4 can be used as inputs also, plus another 4 inputs are possible using the output enable, which caters to all these 4. This is how you get 16 R4. So this example of how devices sort of organized and very versatile. You see, I have registers, I have programmable features, so I can increase the number of inputs, and I have a clock, I have an output enable function, and what else do you need? I can a moderate size design of a sequential circuit, which is driven by a combination logic, can be designed using this and implemented using a single chip. So that is the beauty of the programmable array logic. All these features are developed in programmable array logic. Even though programmable logic array can also be done with all these features, because historically, as I said, from PROM they came to programmable logic array, and then they realized it is too difficult. They moved on to programmable array logic quickly, and all the developments and further work happened around programmable array logic, and that became an industry popular device. And once something becomes popular in industry, they keep on adding features so that they want to sell more and more of them to the industry. That is why these are common. One other device I will quickly introduce to you, I am not going to spend a lot of time on it, is 22V10. Again, it is a generic device, can be made by different manufacturers. 22 stands for the number of inputs, 10 stands for outputs. So some sort of a gimmick has to be done, not to get all those, but I am just going to write only the major features. 12 dedicated inputs, that means they cannot be used as outputs. Dedicated inputs, 10 programmed I/O. That is how you get 22. 10 of them are programmed, 12 are dedicated input wise. Each of these programmed I/O is also connected to 10 D flip flops. So this is again common feature. A given pin can be used as a programmed I/O pin or a flip flop pin by a proper logic inside. So 10 D flip flop, and each of them is driven by a OR gate combination as here. Then each of the flip flop, each of the OR gates, each combinational or AND gate can have, or not each, AND gates can have input 8 to 16 inputs. So output can be registered or output combinations, or output, registered output, IO output. I am not going to talk further about this. You can look up in any standard textbook or in any manual which lists the programmable logic. There are lots of manuals for programmable logic devices. Today you can go to web and search for this. All the major manufacturers have websites in which they give the parts manufactured by them. Look up under 22 VTAN and find out these features further. But what I want to say is quickly is these outputs are very nicely done. We have a combination. There is a little block at each output. This block decides whether the output is a combinational output with combination can be OR or NOR. I can have an OR or an OR output, or I can have a registered output. There is a multiplexer which is there between OR output, NOR output, registered output. Again, register can be either Q or Q bar, or I don't want any of these. I can go for input option. All of these things are possible. So this is an extra nice logic at the output of each of the pins. These stun pins, which are used as programmable IO as well as stun D flip flops. All these stun pins have up anywhere from 8 to 16 gates. Each one has a fixed number of gates. Plus they have this feature. So it's a very, very interesting and useful device. Maybe we will later on have a chance to look at this as in an example. We will stop here for today.